world. Um, we're on a new problem today, 60.9. That one alone should be pretty straightforward. So it looks like I haven't started any of this or read this. We're in the plane, rectangular coordinates. Lattice points would be like points on the grid, just integer coordinates. Line parallel to 1. That passes through. Okay, so that's called a street. So we're picturing like, no, yeah, picturing horizontal lines and vertical lines and calling them street if they pass through, an integer coordinate. The network, lattice points are street corners, sure. The network divides the plane into square blocks, sure. Let R and S be non-negative integers. The shortest path between the origin and the point RS is of length n. Okay. So that's not unique, right? There's multiple. Like if you were at the shortest path to, I guess the shortest path to something directly on the x-axis or the y-axis, that's unique. But as soon as you have both non-negative x and y, so if R and S are both non-zero, you immediately get, at least two answers. You get sort of multiple answers. Number of zigzag paths. This is a zigzag path. The area under the path. What? The area under the path is included by the path. Okay. The horizontal I don't know what you're saying. So like R is the x coordinate. That gives you a vertical line, sure. The area under the path, I guess it's just weird phrasing. I think I know what he means. The horizontal street and the vertical street. Does he talk about the area later or something? Oh, I see. Number of inversions generated equals the area. Huh. And 10 also talks about the area. Well, in any case, so I think an obvious way to approach this, right? Here's your origin. Suppose you're trying to get to RS. So like, this is R, and this is S. I could have done a more interesting example, but the only conditions are that R and S are non-negative. But yeah, you could go north, east, east, east. You could go east, north, east, east. So you can see, like, you're going to need to take R steps to the east and S steps north. So you can think of it as a series of E's and N's in some order, right? So you sort of like, this should be pretty easy to count. The problem with this is just that you don't want to you don't want to overcount by treating these as distinct objects if you change the order of the E's. But yeah, basically I would think you're doing something like, well, like in this example, if you had 3 to the east and 1 to the north, you're just selecting where to put the north, right? So you get 4 options. But more generally, well, all right. I guess the reason that you have 4 options is that there were 3 E's, right? So there's a position before and after each E, and that leaves you with 4. More generally, if you had R E's, we're sort of selecting right? Say you have a bunch of them, you have 5 E's. That means we have 6 slots potentially to choose from. Out of the 6 positions, choose where to put your SNs. So we could do, so yeah, my first instinct is to say something like that, but that's going to be wrong, I'm pretty sure. If we had another extreme, like what if S was like 4 and R was like 2, right? So here's a typical path to get to 2, 4. Yeah, this makes no sense. My formula is not consistent with this type of. It almost went the other way, right? I was thinking you could take 5, choose 2. Like I'm just selecting out of the 5 blank positions around the ends. Select 2 of them to be where you put the E's. But it's probably also wrong. So like, did it work for this? 4 choose 1. Yeah, 4 choose 1 worked fine. If we do it with 2 ends, does it give you the correct answer? Like I would have thought it was 4 choose 2, which is yeah. What's going on, Fembox? Yeah, this is straightforward. This is something more like you'd see in a really basic combinatorics class. I'm sure I've seen this before. I don't know if I've ever taught it, but it sounds like something that would pop up in discrete math. So yeah, he talks about lattice points, and then he describes, well, he lets the sum be n. So if you're on a corner, the sum of the 2 coordinates is n. And then the first question is just how many paths, well, how many shortest paths are there from the origin to your point. And I'm supposed to get this, but I just haven't sorted it out yet. Should be pretty obvious, but so if I had like 2 ends, yeah, part of my problem is these can be next to each other, and I didn't account for that when I'm thinking like, I was picking just one or the other. I was doing something like this, which is not right, but I'm seeing now, All right, so we know we're going to have these positions, r plus s of them. Sort of like n decisions to make. Oh yeah, no, you're right. It is 6. It is 6 choose 2. But I was for some reason thinking like around these we would have blanks, and then I would come back and select places for the e's. But yeah, this is wrong. This is wrong too. All these are going to be wrong. I just haven't thought about it correctly yet. So we do have 11 positions to fill, and out of those positions, select... Oh yeah, that's obvious. Okay. Let's say 11 positions. You have n positions to fill. Yeah, this is obvious. There's nothing really to say. I wonder what his answer is. It's obvious. Okay, sure. Obvious for this, and then use this relation to pass from n to n plus 1. Am I looking at the right? Oh, he's just proving it by induction. Okay. Well, I mean, I didn't do that. You don't need to do that. Out of the n different, like, sets of either e or n, select, say, r of them to be an e. And then that immediately selects the others. So that's it. There's nothing else to really say. This is kind of an obvious answer. Okay, I see. Yeah, that one's pretty straightforward. I don't know why he's talking about proving it by induction. It is obvious for 0, but like... I mean, I guess that's a thought. You could prove it by induction. I don't know why you would, though. I guess it's good to know. Alright. So that was 60.9 is this kind of logic. 10. Number of paths. The number of zigzag paths. What? The number of those paths between the corners, the area under which is alpha. Okay, I see. Equals blah. And by C and whatever, he means this previous... we had done a problem... right, we had done a problem where we look at the Gaussian binomial coefficients and you show that it's a polynomial. Although I really don't remember what the coefficients were. Yeah, and in those 6 you had to choose 2 of them to be north moves. Yep, exactly. Yeah, that's, yeah, right. That's, so I guess this is like a combinatorial proof, what you just said. He did it by induction for some reason, I guess just to be different. I'm sure people are familiar with what we just said. I thought that was more straightforward. But he's saying you could also... Well, I guess the first thing he said, yeah, he said when R is 0 or S is 0, use this remark combined with Pascal's identity, basically. So another proof of this would be like, I mean, another proof of it would be that it's obvious that there is one path when, if you let R or S be 0. So that's kind of obvious. And then, but that doesn't really cover, like he then says we can pass to n plus 1 by using this kind of formula. Which is not exactly how induction works. I mean, it's more like, so we know it's true for R equal to 1 or S equal to 1, and that's all the ways that n can be 1. So we know it's true for n equal 1. To get here, I mean, I guess that's okay. So the n plus 1 case, like, we've got this case and this case covered. That's the base case. Then if you went to n plus 1, or I mean in this case 2, I mean, I know that we're considering these spots, but he's saying you can just use this to transfer from, I mean, I guess this also includes this case, right? It's very confusing. Can street up to the origins at the top. They go down left and right, and labeled with a binomial coefficient of Pascal's triangle. Oh, yeah. Huh. Right. Oh, yeah. Fair enough. Huh. I hadn't noticed that. That makes sense, obviously. Yeah. Binomial coefficients. Yeah, that's cool. That's a cute trick. So like, yeah, 1, 2, 1. And we'll get like 1, 3. So yeah, 3 choose 2, 3, 1, like that. Interesting. I don't quite follow what he's saying with the induction thing. I was going to ignore it because it's obvious. Like, I would not have done it that way at all to do 60.9. I would just read it and be like, yeah, you have n positions and you're selecting either R or S of them, and that's it. End of conversation. But he says something about induction, which is good, but like, what on earth is he talking about? Like, this is the number of ways. This is kind of the object. I don't really see how we get from here to there, but this is true. So yeah, this has to make sense sort of directly, not just be true. Like, So never mind this, but we know that the formula n choose r is true for n equal to 0, say. And it's true for n equal to 1. It's actually, well, okay, it's true for n equal to 1. And I suppose, right, well, anyway, we immediately have that r is less than n, less than or equal to n. But, like, if you want to pass to this case, it's either that r went up by 1 or it didn't? Is that what it's saying? Like, either s went up by 1 or r went up by 1. When you get here, you have a new r value. Maybe that's all there is to it. I guess that's it. So yeah, let me just read his thing one last time. Passing from n to n plus 1. I guess that's all. So as you get to n plus 1, I feel like your r value has increased. He didn't mention that in this one line, but either your r has increased or your s has increased. But wait a minute. If r increased, this doesn't really make sense anymore because it's still the smaller value of n. Like what I'm saying, suppose we had 1 over here. You can't just go like, okay, 2 choose 2 is the same as 1 choose 2. Right? Well, actually, you can. Damn. Maybe that was a bad example. Okay, fine. So what if r was like 0? Or, yeah, what if r had initially been 0? Then you're looking at this. R goes up, comes from either r going up or r staying 0. Alright, I guess you could do it by induction as well. That's probably somewhat, I mean, I guess if you had to do this in like higher dimensions, something like this might be more useful, this argument. But yeah, it seems like implicit in this line is that r increased by 1 as you went from n to n plus 1. Either r increased or it didn't. don't know why that looks so weird to me. But yeah, if you went up by 1, then either S increased or R increased. Alright, I'll move on. 6010 is going to be brutal. And then what? Is this a separate conversation? In order to specify one of the paths, we view in succession unit segments of which consists starting with 0, and we write x or y according to the segment. Sure, this is just the same thing I did over here, east and north. So ends at 4, 3. Yeah, correct. So he's using x instead of east and y instead of north. Take any two letters, they form an inversion. What? Oh, if and only if they're different and y comes before x. In our above example, there's 4 inversions. What? Y comes before x. I'm a little lost. He's showing us that he's basically explaining 11. Oh, yeah. That's good. That's kind of a good point, right? What you just said. Yeah, I hadn't thought of it that way. Huh. I don't know why I never noticed that. Like, if you want this cell, it comes from, what is this, the first? So it comes from these. No wonder it's called Pascal's identity. Yeah, I never made that connection. Good comment. I always just thought of this as like, combinations. If you have this many objects, you either, you focus on one and you say you either included it or you didn't. So that one extra, it's like, here you've included it, so you still have R minus 1 more to choose from the remaining guys. Or if you chose not to include it, then here's you counting all the ways to not include that one extra element. But in any case, yeah, it also kind of just is. It's what's happening in Pascal's triangle too, if you go from one row to the previous. Interesting. So 6010 is a nightmare to me because I'm not super comfortable with, like, we had done on 60.5, I guess we'll call this a review, but the question on 60.5 was to show that the Gaussian binomial coefficients that you get when you do this business are actually polynomials. So if we go to like k times n minus k, I mean, it's conceivable. Anyway, you get some coefficient here that depends on n and k and whatever your power of, I guess he put an alpha here. So here's q to the alpha. Alright, yeah, that's reasonable. So for some reason our index is alpha. But whatever. I don't remember, like, it's obvious for 1, like if k is 1, it's clear, because you just get a geometric series. And like, upstairs you get a sum, right, of these powers. Same thing downstairs. Downstairs is a lot easier to look at. So the denominator's degree is something like, well, anyway, it's k plus 1 times k over 2, I want to say. The numerator's degree is the same kind of computation, but you're going from this number up to n. So however you want to handle that. You could do this minus and the same thing, but with an n minus k plus 1. There's definitely an easier way to do that. You could just do, we know that there's k terms here. Yeah, you could do this. I'll finish my thought, I guess. Wait a minute. Oh no, that's okay. It's okay what you did. That's fine. It's just a little ugly. So it's true that it's this, but that's a bit of a mess. Another way you could do it is to just add these. You'll get 2n minus k plus 1, and that's going to keep happening. And how many terms do you have? I guess not k, but k over 2, if you're going to do it that way. So another way to think about it would be like 2n minus k plus 1 times k over 2. That's the numerator's degree. And if you subtract these, you'll get the degree overall, which is evidently k times n minus k. If you subtract these, you'll get 2n minus k plus 1 times k over 2. So 2n minus 2k over 2 times k. So k times n minus k should be the degree. Yep, should be the degree that you get, which is what he claimed. Yeah, it's yeah, I like fountain pens. This is an old Esterbrook, but for some reason it's leaky right now, so I stopped using it for the moment. I don't know what. I don't know where the ink's coming from. Yeah, got more on me already. That was fast. Weird. Anyway, I don't want to get any ink on this book, so I put the Esterbrook down. But I don't know where. Man, there must be ink all over the place. Yeah, there's ink on the cap too. Weird. Well, I'll get over it. So yeah, this is an Esterbrook. This is a Pelican. Yeah, for the moment it's a nice book, until I get ink all over it. I guess if it's only on the outside cover, I'll be able to clean that up. Anyway, yeah, this is an old red Esterbrook I used to use. So yeah, I got the degree right, and I noticed that like for k equal to 1, it's sort of obvious that it's a polynomial. For higher values of k, you know, you get multiple I mean, it's still somewhat, I don't know how clear it is. We were sort of using a similar argument yesterday when I was doing some problem. 60 point 7. Whatever. But I was basically just using the fact that this will divide, like each term down here in the denominator, it will divide something in the numerator. You can even pick them like one at a time. There's like a 1-to-1 correspondence between a factor in the denominator and a factor that it divides in the numerator. But I'm somehow still not, like it's not super obvious to me. In his explanation of 60.5, the polynomial thing, yeah, it's obvious for the extreme cases. For the rest, he says, use 60.4 and induction. And then the symmetry part, the fact that these coefficients are symmetric, you can just look at it again, but for 1 over q instead of q. And you'll, so I had a video about that a couple days ago. 60.4 is, 60.4 is our Pascal's identity analog. Yeah, these are called Gaussian binomial coefficients. I don't have another name for them. I didn't look it up. I probably should. Because that's kind of a mouthful. I guess it's also just called Gaussian coefficients. Gaussian polynomials. Gaussian numbers. They are Q analogs of binomial coefficients. And yep, brackets instead of parentheses. And here's, if you pull up the Wikipedia page, here's the formula, of course, but what the, yeah, right, q at 1 you would get a sum of k. But otherwise, this is just, why is he just looking at one term? Oh, this is called a Q number? I see. I see. This thing keeps coming up again and again. This form, this ratio, which is I keep just referring it to as a finite geometric series, or it's just this geometric sum. But I guess it's called a Q bracket. Q number of n, Q bracket of n. Anyway, so yeah, so some examples. When k is 1, it's really easy. You just get one term or two terms or three terms, whatever n is. And then whenever k is, you have that many factors in the numerator and denominator. And you're going to get polynomials every time. They're symmetric. So here's a good big example. Yeah. Yeah, Q brackets of n. I mean, that's because it's good it has a name. Anyway, it became, so we did this back on, so yeah, that's what this section has been about. And we did 60.5 like last week. He said to just, okay, so I guess I'm still a little lost. He just used this identity to prove it. He says obvious for the extreme cases, and then in general use induction and this statement. That was how he got the polynomial statement, like proving that this is a polynomial. I mean, I guess that's fine. Because it's easy to see for small n, right? It's going to be easy to prove it for n being 0 or 1. And once you know that these are polynomials, and there's just another polynomial, so of course n plus 1. So yeah, like 60.5 looks pretty scary, but like, you saw me already verify what the degree is supposed to be. And it's still consistent with this statement, so yeah, it's a polynomial. Not much more to say about it. Man. All right, so 60.10 says number of paths whose area is alpha equals these coefficients in this polynomial. That's very... okay. That's crazy. I mean, okay, my problem with that is that I didn't really solve for them. I mean, all right, I guess we can... you know what I mean? I proved that it was a polynomial, but I never actually like thought about what the coefficients are. But I mean, I guess they come just recursively from this identity, if you want. Yeah, if you don't do it that way, it's kind of a nightmare. If you try to just do it directly from the formula, I don't see that happening, because you get a bunch of finite geometric sums, and you sort of, it's the product of those in Q. So there's a lot of combinatorics going on. So a better way to think about these coefficients is probably just using this identity somehow. All right. Those paths between, 0 to RS, the area under which is alpha equals this coefficient. I'm sure he gives us, he gives us a fast explanation. Damn it, it's like a one sentence. He refers to our happy little identity again. What is it? N. Here, I'll show you the answer since I'm... whoa. So 60.9 says it's pretty obvious for 0. Or for r times n minus r. Anyway, use these cases, 60.4 and induction. Okay. Okay, fine. Here's 60.4 again. And then... where is it? Alright, fine, whatever. K minus 1 times q to the n minus k plus 1, yeah. So this is what he means by 60.4. And I guess he wrote an article about this in 1969. Yeah. He sure did. He would have been like 81. How? Oh yeah, 69. Okay, fair enough. Isn't this book from like... yeah, the book was written in 24. And then this I mean, I don't know when this was printed, but I think it's from 70. Yeah, this is the 78 edition. So, okay. See, that's confusing to me because this was an update. Like, I wonder what the 1924 edition originally said about this problem, since he obviously he hadn't written it at that time. This is him back in 1925. But, all right. Anyway. Number of paths whose area is alpha is equal to this coefficient. And then he claimed it was obvious for 0 and for alpha being 0 and for alpha being something like n times n minus r times n minus r, I see. Alright, so the 0 case, I'm a little confused by these areas. He told me about it. The area under path is included by the path. Okay, so it's just your typical idea of area. So the 0 case is everything where it's like flat or it's vertical. That's about it. And in that case, I mean, the coefficients are supposed to be given by, oh, you said the coefficients of this. CNR alpha. CNR alpha, which is like if we had this, we know that this is, oh, that's why he says Rn minus R. Okay. So here's the coefficients that we're talking about. Let's just call them alpha. Q to the alpha. So when you expand this, you get some coefficients, and the two cases on the ends, I mean, I would assume those would be 1, but I'm supposed to get 0 for them? Oh, the number of paths between whose area is 0. Okay, so there's a bunch. From 0 to RS. Okay, so if we were at like RS over here, well, alright, I'm a little confused. The area under the zigzag path is included by the path, the horizontal axis, and the vertical axis. Oh, the vertical line, x equals r. So like this. Yeah, I don't understand these areas. Oh, is there only the one? So it still has to be a path all the way to RS. I was picturing a bunch that happened to have area 0, but they weren't going to RS. They were just going to like wherever. They were just going to... I was keeping S to be 0, for instance. But it seems like I do still need to make the path go there. So we should think of like, there's only one path that can do that. That's the one I just drew here. It's like, you know, x, 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 x with a y on the end, if you're using his notation, or, you know, strictly east, and then at the very end you take a north. So I think that's got area 0. Because he only mentions this vertical line. He doesn't talk about the y. axis. He talks about the x-axis, so it's like area to the x-axis, but under your curve. So in this case, it's just 0. This area would be 0. And I guess there's only 1, and that's telling me that this is 1. The other extreme would be this guy is also supposed to be 1. Well, he didn't say that, but no, he didn't say that. This was area 0, and I'm assuming that it's 1 because I only saw one path. The other one, this is the area, r times s. So this is the other extreme, right? This is like you went up and to the right. That's your path. And so this is your area. And so, of course, you're getting r times n minus r is the area. And there's only one way to get that, too. And these are symmetric, so that makes sense. Okay, so those are the two easy cases. And then it is symmetric, which kind of makes sense. It's consistent with this. So, like, you know, if you did this, it's the same area as if you... Wait a minute. This isn't going to work. No, it's not the same area. I'm saying the number of paths that do this is the same as, like, the number of paths that do this. It's not that it's the same area. The area is, it's the same number of paths, and your area is this index. So I guess they're symmetric about this total sum. If you took like this minus s, it's the same as s. Like that's the number, the number of paths is the same. So if you had an area of like 7, well, anyway, if we did an example like 2 steps up and 4 steps to the right, then in this case, n is 6, and the maximum area you could have is 8, right? Right, just 8. So the two easy examples are like C0 is 1, there's only one way to do that, and that's just going to the right and going up. Or if you just take this whole block under it, you'll get 8. So C8 is 1. But what I was trying to say is, like, we also have that C1 equals C7, meaning the number of paths with area 1 in this picture is equal to the number of paths with area 7. How do you even get an area of 1 in this picture? How? Oh, I see. Yeah. You do this. You basically do that kind of thing. So if this is 2 steps up, if this is 4, 2, you go all the way up to 3. You go up. So there's your 1 area. So that's how you get an area of 1, and the number of ways to do that is the same as if you had done 7. So like if you had done, well, this kind of thing. Well, sort of. Yeah, it's similar to this. 7 would look like 1 up, 1 right, 1 up, and then you go the rest of the way. So here's 7. Here's 1. All right, well, at least it seems feasible, right? It seems possible. curved paths between street corners whose area is alpha is equal to these coefficients. These coefficients. The ones that come from these Gaussian binomial coefficients. And he said it was easy. He said to just first of all observe this, and then use induction and use this Pascal's identity analog. It's obvious for 0 or the maximal area. Use those cases and 6.4 and induction. Great. Well, I'm glad there's answers in this book, because I would have had no idea where to start. But at least he's given me a direction. 6010 said the following. Say you're at point R. Actually, it doesn't say that, but let's, for instance, say RS. The area under a particular path is just the usual area that you would think of. It's like capped from the bottom at y equals 0, and it's capped on the right-hand side by x equals r. And so if you have a path that goes like this, you just sum up each block. These are each unit blocks, you know? So you just get the area under that curve. So his statement was the number of paths going to RS with area alpha is given by basically C alpha in this crazy formula. We're going to have NR you basically just get the coefficients that come from this polynomial. And this polynomial is along, I can show you an example though, we looked it up earlier. God damn it, this is not it. Here, I'll show you. It's not Q bracket. How about if we look for Gaussian binomial, okay? That's what we're talking about in this chapter. And it's this notation with brackets. And it's this formula, which looks a little crazy, but if you'll notice, the number on the bottom, or k, if you're doing k, you have k factors, both on the top and the bottom. So that helps. Yeah, it's very much like n choose r. This is a generalization of the binomial coefficients that you're used to. I guess it's called, apparently this is a common thing, called a Q number, or a Q analog. So like, well, anyway, here's some examples down here. Like, it's not literally choose because it's a different formula, but it's a generalization of the normal. So you know what? I think if you replace Q with 1, you might get regular binomial coefficients back. And I realize it looks like it doesn't make sense. So like here you'll get 1. 3 choose 1, you'll get 3. So you see what I mean, sort of? If you let Q equal 1, I think it's gonna agree with the usual number. So here's a way for us to test it. 4 choose 2 should be 4 factorial over 4. So it's basically 6. And if you sum this up, you'll get 2 plus 2 plus 2. You'll get 6. So yeah, it is. Yeah, are inversions just paths? I thought inversions, like, are these each inversion of 6? I don't know. That's my instinct, but I don't really know what inversions are. I assumed it would be every combination. Something like that. Oh, okay. Yeah, Dave's losing the plot now. So let's get back. So this he just told us, actually. This was an earlier result, which I'm not going to show you because I'm covered in ink. But Pascal's identity with binomial coefficients, you can prove it for this thing as well. It's just a little different. Sorry, not this. Here it is. It's got a little factor of q over here. This is not the way he wrote it. Huh. He had like n minus k plus 1 here. Anyway, and Q analog, I didn't really read this closely, but a Q analog of a result, like say you know about the binomial theorem, right? The Q analog, or say you know about binomial coefficients, would be a little easier to talk about. A Q analog would be that you introduce a parameter Q that gives you back the original result when you let Q go to 1. So that's like a common trick in math, is you look at sort of, you look at something that's maybe like a weaker statement because it involves a situation that isn't 1. Like maybe the case when you let Q be 1 is very difficult to understand, but you can understand the case when Q is less than 1. So you do what you can with that, and then you try to take a limit. That's sort of the idea. Kind of waving my hands there, but yeah, it's using the same notation as binomial coefficients because it's the Q analog of a binomial coefficient. To count the paths, that's not so bad, but Pólya's next question was like, all right, well, think about the paths that have a particular area. We're going to fix the area as alpha. So like an easy one would be like, how many paths have an area of 0? Well, let's do a real example. So say you have like, you go out to 4 and you go up to 2. So we're talking about all paths that land there. Now plenty of them have area. The most extreme case would be is if you go up twice and you go over 4. That's the biggest area you can get. We'll call that north, north, east, 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 okay? This has area 8. It's this area. But another way to get there, the other extreme, would be to go over 4 steps and up 2. So if we start off going east and then we go north, this has area 0. Anyway, he wants us to count the number of ways that you can get these particular areas. So like, there's only one way to get an area of 0, actually. And there's only one way to get this maximal area. So if you're calling this RS, and you're letting n be the sum, we've noticed that this area is R times S, right? It's R this direction and S this direction. But S is n minus R. So this is this area, and this is this other area. And so anyway, so the two extremes are that he's saying there's a coefficient that gives you the number of paths. And the first thing he does is point out that for these two extreme cases, it's easy. You just get 1 in both of those cases. And that's about where my understanding ends on this problem. I'll show you what he does next, but he basically uses this again, this identity, to get from m minus 1 to m. Although for some reason in the book, his identity looks different. It's probably the paper that I crumpled up minutes ago. Hey, my thing's still writing. It's this guy. So yeah, he's got a different power up here. Oh, No, maybe he doesn't. Yeah, it's different. It feels different to me. So like, see how... Maybe it's not different. So he starts, well, you can't read it, but here. I'll write down what he says. This is his identity, the one I've been using all along. It's evidently the same that's in Wikipedia, but it doesn't look quite the same to me. Okay, so I jotted that down. And we're working on 6010. He points out that the total number of course it's frozen again. Anyway, it's this, yep, what on earth? Let's see if we can fix this. There we go. We're back in business. The coefficients that he's talking about are coming from this polynomial. I'll show you on Wikipedia. If you scroll down, oh, never mind, I went too far. Yeah, these examples. This, like every time you do one of these bracket things, you know, it reminds you of a binomial coefficient, but they're called Gaussian binomial coefficients. But anyway, when you do them, there's a q involved, right? And if you just plug numbers in, you get numbers. Well, anyway, there's a q involved. The point is that they're polynomials. They look like this. They start off as this definition, but you can show that they're always just a polynomial. So like here, we'll do 4, 2 in q, and you get this mess. Like it starts off as this by the definition. It's this ratio. You get 2 factors on top and 2 factors on the bottom. But you can show that you will get a polynomial. So these are the coefficients that he's talking about. I was just showing you guys, like, it's called C alpha. He's saying that C alpha is the number of paths that have area alpha, where C alpha is these coefficients that you see. So if, you know, suppose we had RS like 6. Here's a case where R is 3, right? He's saying that these coefficients are giving you the areas. Like, here's 1, those are the two extremes. And then if you want an area of, say, well, okay. In the 6, 3 case, we're saying both R and S are 3. Like that's 3 steps to the right and 3 steps up. And so the easy cases, the only ones I've mentioned so far, is that like C0, this is all the ways that you can have an area of 0. And then 9, does that make sense? 3 times 3 is the area, I guess, in that case. So 9 is another area. There's only one way to make that happen. But apparently there's only one way to make 8 happen as well. The only other thing I know more than you guys about this situation is that this is symmetric. These coefficients are always symmetric. So here it's like 1, 1, 2, 1, 1. Here it's 1, 1, 2, 3, 3, 3, 3, 2, 1, 1. It's symmetric. Does that make sense? The coefficients themselves have symmetry. So that means I know that like what's the maximum 9 and the min 0. So that means I know out the gate that the number of ways to get an area of 8 is the same as the number of ways to get an area of 1. Number of ways to get an area under the paths is 7, is the same as the number of ways to get an area of 2. And you can kind of see that. You can kind of feel that that's true, even if you don't know any of the formulas. When you draw this stuff, right? If I wanted, okay, it's done now for real. Let's try this guy, I guess. Actually, let's have fun with it. Try our fancy Monteverde guy. You can kind of see that that's true, even if you don't know much about math. Like, Yeah, yeah, yeah. What you just said. Just swap the e's and the n's. Exactly. Yeah, yeah. It's very symmetric just by drawing it. So we were looking in the 3 by 3 case. Yeah, it's exactly what you just said, Fembox. You're not? I think you're right. So like, let's draw one. Here's a box 1. Let's just do this. Well, this is a stupid case. Why'd you pick the 1 right in the middle? Yeah, don't do that. Well, that's not the point. So the area here would be 1 plus 2 plus 3. So this area is 6 to get to 3, 3. So I drew one way that you could have an area of 6. But apparently from the numbers, let me pull this up again. 6 has a coefficient 3. So there must be 3 total ways to get this area. Yeah, you're right. You're right. You're wrong. You were wrong the first time. I guess. What I was going to say was exactly what you just said. I was going to point out that, like, if you know that, like, well, okay, the easy cases is like what we did over here. Like, you know that this is a path. Its opposite is this. So that's why there's like a 1-to-1 correspondence there. So yeah, just flip the e's and the n's, and you'll get all the other cases. So you're right. It doesn't tell you how many there are, but it tells you that it's symmetric. So that observation, you know, even without really knowing any math, just looking at the graph, you can see. Oh yeah, sure. Yeah. I like that. That makes sense, Fembox. Yep. That's cool. That's smart. That also doesn't take much math. I like that. So yeah, when we draw this, its analog has the complement area, right? Yeah, that's smart. Which still doesn't help me count. That's fine. Anyway, the way he had actually proven the result, because he's saying you can just get it from the polynomial. Like, to count the paths, all you have to do is get these coefficients, which is easier said than done. But yeah. Yeah, I suppose you're right. It's just a rotation. But yeah, how else would we get 6? I guess I just don't see the connection between the two, and I don't think I'm going to, because his proof involved this identity. He basically just proves it by induction. He's like, look at this simple case of 0, and then use induction, and ta-da, we're done. Which didn't make a ton of sense to me. Well, it does and it doesn't. He's doing induction on n, obviously, but I was a little annoyed because you have all these other cases. Like, you have a bunch of cases for k from 0 to n. But, you know, yes, it's true for n equals 0. N is true for n equal 1. And so we can probably move on from there. But yeah, he somehow uses induction. Wikipedia says that this identity, Wikipedia phrases it this way. MR is QR times M minus 1R plus M minus 1 R minus 1. That's what Wikipedia says. I don't... So the other thing, well, I mean, I guess that's fine. These are symmetric, again. You know, it's true that this is the same as this. So I guess that's all that's happening here. I was just confused that Pólya likes to use this minus that, and Wikipedia just used the bottom part. So I was already like, that's not the same number. But, I mean, it's true, it's not. But, Yeah, that's weird, right? In Pólya's case, he did n minus that number. But in Wikipedia's case, they didn't do that at all. They just used that number. You see why I'm kind of annoyed? So it has to just be this somehow, but I don't quite see it. Anyway. Oh, are they both true? Sorry, I'm just realizing I missed the second line. The second line is Pólya's form. Yeah. Well, almost. Almost. Pólya's form has a -1 here. He says q to the m minus r minus, plus 1. Plus 1. So Pólya's is a little different. It's very frustrating. How can it be wrong? Like, Pólya's is literally this times q. There's an extra q. Oh, wait a minute. I'm being dumb. No, it's the same. So this is identical to Pólya's. Sorry. Pólya's has an m plus 1 here and an m's. So that's why it's different. Okay, good. So yeah, this second form is the one Pólya has in the book. This first one, I didn't realize. Oh, it's not identical. It's here. Like these are the same somehow, because it's not actually written the same. He put the q here. Okay, I guess I could see that maybe being true. If we multiply by q, you just get. That's weird. I'm confused, man. So yeah, 60.4 makes sense. Induction makes sense. Oh yeah, 60.4 was. We can talk about it. It'll be good for me also. Actually, it's probably better if we just look at his answer. There's two reasons. I did it like from scratch the other day. He just used he used a previous result. His answer is not going to be very satisfying because you would need to know 60.3. I proved it a different way when I did this one. I just did it by induction, I think. But he uses this. He proves this. We would prove this earlier result, which is actually not as bad as it looks. But if you treat this thing on the left as a function, you can write down a functional equation that it satisfies. So like, think of this thing on the left, and instead of x, plug in q times x. Like, take f of qx. And what's going to happen is it's going to shift, right? It's basically the same function. So take a glance at 60.3. And then it happens to satisfy this equation. So if you use that along with the fact that it's a series, if you use that and you assume that there is some power series for it, you'll get these coefficients. And then once you have that result, you can kind of tweak it to get this. So maybe it's a long story. You basically just take the result from 60.3 that we were just talking about, and you multiply by one extra factor, the last factor, and it bumps your degree up from n to n plus 1 in the formula. And then you can just equate them, and this is the statement that you'll get when you equate the coefficients. So it's a mouthful. It takes a minute to prove, but I had done it differently. I think I had tried to do it just directly from the definition. But I don't remember how easy or hard it was. I had a video on that last week. What is going on here? fair enough. Ditched all my stuff. I think it's still writing. It has plenty of ink in it. All right, good. Yeah, so we said this is the same as. Oh wait, no, we didn't. Well, all right. The way he does it is like n plus 1 is nk plus q to the n minus k plus 1. Like that is the way he did it. Yep. It's the same as the second form on Wikipedia. Anyway, so we noticed that if you look at, well, we were doing a specific case of like 3-3, or I guess it's 6-3. So I'm just going to copy this from Wikipedia. They happen to do this example. Oops, damn it. It's 2q squared, 3q cubed. Then you got a bunch of 3's. Three q6, and then 7, 8, 9 is 2q7. Oh, sorry, not 8. 1q8 and 1q9. And so we can magically use these numbers, these coefficients, to tell us the number of paths that have a particular area. But that still seems magic to me. I just don't. I guess even though I know the definition of this thing, like, so 6-3 would be 1 minus q to the 6, 1 minus q to the 5, 1 minus q to the 4. And then downstairs, you do this. And that just seems like magic to me. But evidently you can pair them off in such a way that it's the product of a couple different, it's the product of 3 different geometric sums. They're not very long. And you get this. In fact, we'll look at it here. So yeah, this is the definition. But you can pair these in such a way that, like, so like 2 can go with 4, and you get 1 plus q squared. 1 minus q to the 6 over 1 minus q cubed would give you just 1 plus q cubed. And then these guys pair together to give you this. Yeah, right. Yeah, 4 with 2, yep. So indeed, you can certainly pair them. And I did a stream like yesterday where it was a little hand wavy at first, but I eventually realized you can just always do this. That's not the way he proved it. So like what we're observing right now is that you'll always get a polynomial. You will always get a polynomial. It'll have symmetric coefficients. That was actually one of the exercises we did recently. But so that was problem 60.5. And that's what we're using for this junk, because he wants those coefficients to give us answers. So yeah, he had us show this. I kind of did it, I almost did it directly. Like, I just looked at the definition and I said, look, you're always going to be able to pair these things. It wasn't quite that simple. There's like one little hang up, but for the most part, yeah, you can always just pair them. He did it by induction. And he used the previous result, the identity. He used that Pascal's identity again. Oh, here it is, 60.5. So he basically used that Pascal's identity analog again, and he used induction on it. He's been doing that a lot. He loves that identity. It seems to get us a lot of mileage. he seems to be using it again here for this area comment. He basically says, well, the coefficients agree with the number of paths when you let k be 0, or like when you let n be 0, or when you let n be 1. And if you combine that with this statement, you're done. So, I mean, I know I said that like a half hour ago, but I was going to try to prove it. So we're supposed to be seeing easy cases like 0 or 1. 0 is obvious. We don't need to say anything about that one. There's only one way to get an area of 0 when you don't go anywhere. Sure. 1, though, is a little more interesting, at least. You have 2 paths. You can go here, or you can go here. Either way, the area is 0, so you just get 1 coefficient. Seems like a pretty weak hypothesis, but apparently that's enough to get us going. I still don't know what the hell this has to do with these coefficients, but apparently it's all in this formula. That's all it has to do with those coefficients. So yeah, if I was trying to pass from, I mean, shouldn't we have more to go on? Shouldn't I also have like, oh, I'm confused. Oh, okay, I see. So this is the n, the 1, 0 case up here, and this is the 1, 1 case. But either way, the coefficient there is 1, indicating there's one way to get that area. Wait a minute. Isn't this already 2 ways? I guess I'm confused. Alpha 0 in this case. There's only the 1 that I wrote down. But there's definitely 2 paths. Oh, no, there's not. What are you talking about? I see. Sorry. This is actually 2 different examples. This is actually 2 different, totally different examples. Here we're letting R be 1 and S be 0. And here we're letting R be 0 and S be 1. And anyway, you pick 1, you fix 1, then you count the number of paths that have area 0. In this case, it's 1. All right. Anyway, I'm sure we're all on the same page now. Never mind. Back to it. So in the n equals 2 case, there's a few different points you could look at, right? We're going to pick one of them. Huh. It's strange to me. Oh. Yeah, no, it depends on k, doesn't it? Yes, that's right, Fembox. N minus k plus 1. Yeah, sorry, I know you can't read it. N minus k plus 1 times this guy plus this guy gives you the higher one. Yeah. Fancy pen time. I better check this book for signs of ink damage. No ink so far. I'm going to need to start using fancy soap to get this ink off of me. Well, it's usually not a problem. I'm usually not filling them. But anyway. So let's see the way he phrased this. Because it really depends on, see, like he says CNR alpha. He's very cognizant of the fact that it depends on which point you're talking about. So when you're going to RS, that's like one particular, I mean, there's multiple values of n. Never mind. I'm saying there's multiple lattice points which have a fixed n. So it depends very much on R, which, so yeah, this coefficient does depend on R. But I'm kind of acting like it doesn't. I shouldn't be acting that way because I'm trying to fix n, you know? I was trying to like say, we're going to do all the cases where n is a particular value. But like there's a bunch of different cases. There's like R, well, anyway, there's n plus 1. Yeah, is that right? Yeah, there's n plus 1 different cases because it's also all the lattice points on a diagonal. What are we doing? Oh, yeah, like this was his answer for 6010, the question about the areas. If you have an area alpha, he points out that the two extreme cases are easy, you just get one. So use that identity and use induction. And if I ever get through that, that'll be the end of the stream. I mean, at this point, I may as well just do the rest of the book, right? Oh, wow, that's actually the last of... Oh, no, it's not. 6011. There's one more in this section. But yeah, 6010 is this one about the areas. And then he mentions the x's and the y's are basically just e's and n's. I don't know why he used x and y, but... So you could indicate a particular... You could specify a particular path by a sequence. And then he talks about inversions, right? This is what you were saying a little while ago. Take any two letters, they form an inversion if they are different, and y comes before x. I still don't know what the hell he's talking about. Because he says in our example, there's 4 inversions, but like, I see 2. They're different letters, and y comes before x. Take any 2 letters in this sequence. The first y has 2 trailing x's. The y-axis don't have to be adjacent. Oh, I see. Oh, any 2 letters. If y comes before x. Got it, got it, got it. Okay, so like this y with that x. I see. So there's 1, 2, 3, 4. Gotcha. Take any 2 letters in such a sequence. Okay, got it. Not adjacent letters, not sequential letters. Got it, got it, got it. They form an inversion if y is before x and they are different. That's a strange... Oh, is it a strange definition? Maybe not. All right, so what that corresponds to, if I go like east, east, north, east, north, north, east, this with that and this with that, and this or that or that. Got it. So he's listing all the things that we could change and get the same path. Like that's maybe a way to count the paths. No, not quite. Like if we swap this, we'll still end up... Oh no, it's a little more complicated than that, isn't it? Yeah, I don't know what these inversions are good for. Anyway, the comment was number of inversions is equal to the area under the path. Yeah, Yeah, that's a good result. I don't understand it, but it's a good result. So I wonder if I can figure out this stupid induction thing. It should be like basically trivial. I looked at the cases of 0 and 1. Those are obvious, and it's true. When you look at 2, you sort of really should fix because your k is going to be determined by which one of these points you're using. And it's kind of annoying because these two cases are stupid. But if we take the case in the middle, right? These two cases are silly. If I just do like 2, 0, I don't know why this thing won't write very well. Maybe my nib is weird. Anyway, you take like 2, 0, there's only one answer, and you just get one path for the area of 0. Same thing with 0, 2. But I mean, that's good. That corresponds to, like, when you're looking at... No, it's not great. I'm confused again. Each one of these is its own polynomial. Like if I look at this, it's a dumb one, but it's a polynomial. All right, fine. Good. Yeah, I think we're back on target. So if we look at 1, 1, we're looking at this polynomial, and it's probably going to be like, I'm not sure what the guy in the middle is. We could do it out. 1 minus q squared, 1 minus q, oh, no, it's not there, that's not there. So you get this, so this is the polynomial. Really? There's only 2 terms? Yes, there's only 2 terms. All right, fine. So this is the polynomial that you get. And it's telling you you could have an area of 1, but if you do, there's only one path that gives you that. That's already not true. Son of a bitch. Oh no, it is true, it is true. I'm sorry, I got it backwards. Good. So this path, going east and then north, gives you 0 area, and going north and then east gives you another area of 1. So all right, so it's true for n equals 2. We just saw it directly, but I'm still a bit confused by like how I'm going to use this, because like I have a fixed k value, and this formula has a different k value in it. But on the other hand, that's the hypothesis side that has different k values. Like I know it's true for both of these n's. This is the one we're trying to see that this is equal to some coefficient. And on the left-hand side, the coefficient that we get is what? Well, you get different coefficients, okay? So suppose you have a set of coefficients on the right that were, indexed by alpha. Well, you really need to include the n when you do that. But anyway, we know that this is true, and we know that on the left, there's coefficients here, like it's something like q to the n minus k plus 1 times this coefficient plus this coefficient. And evidently, that's this coefficient. I think he didn't have much more to say about it. First y came for the 2 x's. Those are bottom 2 blocks of area, along with the bottom row of the figure. That first y came before a couple of x's. Oh yeah, those are also the first time you get any area, as soon as you first encounter a y. I see what you're saying. Yeah. All right, fair enough. The area is for, oh yeah, right. Every time there's a y with an x. If there's not an x following it, it doesn't actually contribute to our areas. That's true too. Huh. So I have a y and two x's. That's 2 blocks. And it's also 2 inversions. And then if you have another y, as long as it's followed by an x, that'll be another block. It'll be another unit. I guess that's why he went to such pains to describe these unit blocks in our lattice, in our grid. I was like, yeah, that's obvious. Why are you talking about that? But he's hoping that you're looking at a graph because it's helpful when you think about the areas later on. Interesting. This Q being here changes the, I mean, that doesn't matter, but it kind of shifts things. It's weird that that's in the coefficient. This doesn't make sense what I wrote, right? I mean, it's apparently true-ish. No, it doesn't really make sense what I wrote. If you were trying to say something about the coefficients, it's this times the polynomial. So what's happening is this shifts probably this number. You know? So this is a polynomial, and you multiply by q, and it screws with your coefficients. Is it easy enough to just say this? This might be true. That you're just subtracting, you know? If it was like you just multiply by q, it's going to shift everything back. So what used to be 0 is now 1. What used to be alpha, I guess I should be adding. Haven't thought about this very much, clearly, but I guess it's closer to something like this. That this formula is how you get this coefficient. Yeah, it's good. I don't know, I'm frozen again. This is a good time for me to wash my hands for the 3rd time. What am I going to do about this frozen thing again? I guess we'll reset it. Here we go. Are we in business yet? Probably. Man. Yeah. Back to life, droid cam. Alright, there we go. I can't chat. Weird. I'm unable to type anything. I can only communicate through emoji. Well, no problem. I guess I can still speak. No problem, Fembox. It's good stuff. BRB. Yeah, I don't know why this doesn't write as smoothly as it should. If I press a little bit, you can see it skips, right? Someone who's a little smarter with fountain pens could probably fix the nib. I used to sort of tweak them a little bit. Like, you could just bend it a little bit, but you don't usually want to do that. It should have like a tiny bit of space. Yeah, it shouldn't be, it doesn't write as smoothly as it should. Shouldn't have to press at all, and if I actually want it to write, I have to kind of press. But it's kind of a special nib. It's italic, so it is a little bit flexible, but I don't think it's supposed to be dry like this. I don't know. I'll be right back. Well, my hand washing has fixed nothing. I'm still covered in ink. What's going on, eat of the pie? What's going on, Zach? I think it's Zach, right? I want to say Zach. It's my instinct. Yes. Now I'm stalking you to confirm. Welcome in, Zach. Good to see you. I'm on for like 2 hours longer than I should be. I spent like an hour and a half talking about fountain pens. And then I have to like keep them away from the book because I'm all inky. The cover's not bad. I can always watch the cover. Oh yeah, Hagoromo chalk. Yeah, I like chalkboards more than whiteboards, but I'm not going to spend $600 on a chalkboard. So that's why we use paper on Dave's stream. We're doing a pretty cool problem today, but I should basically have finished it already like 3 or 4 times, and I haven't been. I'm kind of putzing around. I still don't really understand what I just... We're going to put this up. It's not as smooth as I need it to be. And this one is dry. We got to figure that out sometime. We could use an SD for a little while. Oh, I was going to fill this one, wasn't I? Did I forget to? I bet I did. Yeah, we can fill it later. Oh, yeah, do you have a chalkboard? Is that in your like home office, I guess? I thought it was a whiteboard, but I haven't been paying attention. This is the material we're sort of looking at today. Has to do with Gaussian coefficients. And, it must be down here, right? It must mention... It doesn't... Maybe I'm too stupid to see that it says it. I think it doesn't say it here, really. It says much higher, much more abstract stuff. Oh, yeah, here. So this is the number of paths, right? It's just talking about partitions. Well... Yeah. This is the same as what we're talking about. Well, we moved on from there. That was like the easy part. Now I was talking about the areas under those paths. Anyway. And all he said was basically just use this, use 60.4. So like use this identity, use induction to pass from n to n plus 1. Huh. So if I know that for the n's, if you were trying to find, say, the number of paths was area alpha, in each of these cases, there's a coefficient for it. And because this one's being scaled, it kind of changes. I think it's going to add to your alpha. So boom, here's my coefficient. So what precisely do I need to show at that point? Like I can see that we'll get, I guess what I'm concerned about is that this is true, what I jotted down. Like, is that actually what you get for this coefficient? But it must be, because that's how we proved the polynomial stuff in the first place, was using this identity. So what I'm saying is, when you do this, this car is a polynomial. Like, you're getting q to the n minus k plus 1 times, I don't want to write it as the original definition, but you get something like this. Is it 0 to, I'm looking at the book now. You get this. So in this formula up here, you can just replace your bracket with this polynomial in q. That's a q to the alpha there. But I guess there's really not much to show. Like, the way we prove this, the coefficients came from this formula. Like, we proved this 60.5, the fact that they're polynomials, we proved it using induction, using this formula. So I guess kind of obviously this is what you get, because I got this from that formula. So maybe there's nothing else to say, I guess. The degree of your polynomial is like, what is it, k times n minus k, which is suddenly seeming like a much more natural number. It's r times s in our new notation. Yeah, and then the coefficients, he's using this n comma k comma alpha, or for us it's n comma r comma alpha. But yeah, you get some coefficient here, which depends on n, depends on k, depends on the power, like that. So if you do that, it's going to add to this number, which I thought was going to subtract from this alpha. Doesn't it? Suppose this was like q. Yeah, it subtracts, doesn't it? So this is a subtraction. I'm pretty sure. That's what I had first. Well. Right? I'm saying that if you took like q times a sum like this, it shifts them back, right? This changes your C alphas to be, it's now C alpha minus 1 is what I'm saying. If you add 1 here, you subtract 1 from the index. Yeah, okay. I was right the first time. It's subtraction. Anyway, it's a moot point. There's not much else to say, I guess, because this coefficient came from this identity, and very weird, man. Very weird. All right. Well, since I've been on so long, we may as well take a look at 6011. Number of inversions is equal to the area under the path. Oh. Yeah, okay. We did look at that. What does he have to say about 11? Aha, he says the same thing. So he says what you said like a half hour ago, Fembox. cut it into vertical strips. He's just doing a geometric, I mean, if you can even call it geometry. He's going to say the same thing you said. So under any path, you've got strips of size 1. He's very confusing phrasing. Yeah, there you go. The area of the strip is the number of Y segments. Exactly. If you don't have a Y segment, you have no thickness. And every time you have a Y segment, it increases by 1. But it's the same thing that you said. He's talking about strips. I don't know. It's the same exact picture that you drew. The Gaussian analogs of polymorphs can be used to determine the number of certain more general letter sequences. And I guess he wrote a small paper about this in 1970. So yeah, 6011 is to just draw a picture. Thanks for your help, Fembox. I had no idea what was going on with those inversions. I guess I might have figured this part out with the graph, but I had no idea what. I didn't understand the inversion definition in the first place. So yeah, 6011 is to sort of draw something like a series of, like, here's x, x, y, x, y, x, say. X, x, y, x, y, x. And every time you have a y followed by any x, that's at least one area. Like, every time you have a y, well, anyway, it's almost easier to just call them inversions now. But if you have a y followed by 2 x's, that's 2 blocks of area being added. If you have a second y, then that's another block, as long as it's followed by an x. Cute. Yeah, they're not bad. I can sort of show you. Well, you could skim my videos on Twitch from the past week. It's just beginning with section 5. It didn't really use any of the previous stuff. So 60.1, 60.2. So like, I'll just show you what's in there. Here's the definition. It's not as bad as it looks. It's 1 minus powers of q. In the denominator, you start at 1, and you increase by 1. And you have, if you're doing n choose k, you have k of those. You also have k factors in the numerator, but those ones start at the higher power n, and they decrease by 1. So if you've only got k of them, you're going to stop at n minus k plus 1. 0 is defined to be 1. Like n choose 0 is defined to be 1. If it's outside of this range, it's defined to be 0. So you have to be in the sort of usual, the typical range. And then, yeah, 60.1, you take a limit. Yeah, 60.1 is a good one because it's kind of the point of this whole tactic. What Wikipedia seems to call Q analogs, and is like a pretty common tactic, and I don't know, I've seen that in like probability and stuff too. Yeah, there's another, so here's some more results. Oh, you can't see them. Here, let me back up. So besides the identity, well, there's also this crazy one. But this had to do with, I mean, I guess it was useful, but it had to do with this, are these called like, no, not cyclotomic, but this had to do with like some earlier function, like this function. But yeah, besides that weird result, you got this identity, which you can use the previous one I just showed you. You can use that sum to prove this. But this one's pretty useful. Then 60.5 is just pointing out that they're always polynomials. That's what you just mentioned. Yeah, he doesn't talk about the sum of those polynomials. But I guess using this result, you could probably conclude what you just said about the sum of the coefficients. Something like that. But there is this one that if you plug in q as -1, you'll get back, well, you don't get back the original, you don't get binomial, but you get binomial of like half r. If r is even, you get something. Okay. Yeah, I forget how we concluded that. Were we just looking at this stuff before? 2, 3, yeah, that's right. We saw it in the examples earlier. But that's just evaluating, right, that's why you brought that up. I see what you're saying. Yes, if you evaluate when q is 1, you'll get regular binomial coefficients, which makes sense. And that's, you're right, that's this result. Yeah, right. I wasn't thinking. But this guy on the left is a polynomial. If you plug in 1, you'll get the sum of the coefficients, and yeah, it's equal to that. So yes. Yep. Yeah, 60.1 is a good one. I wonder what he had to say about it. You have positive integers. Oh, yeah. He's doing the same thing. He just sort of, yeah, he did like a sum on the top and the bottom. And then you plug in 1, and you get evidently L over M. Right, and then the orders change. Yeah. I mean, 60.1, he gives you the main hint for it, but he didn't actually spell it out. But like, the rest of it would be, write down each of these, and you can see that like, you're getting k factorial on the bottom, you're getting n factorial on the top, and you also have to divide by, anyway, so it's clear. 60.1 is clear once you see that trick that he printed. Like, once you recognize this, you can prove it from the definition. 2 is supposed to be obvious. Yeah, is it? Symmetric. They must be pairing up somehow that I didn't notice. I mean, I proved this last week, but I don't remember what I did. if you had, say, 6 and 2. That's 2 factors. And if you have 6 and 4, that's 4 factors. But a few of them cancel, and you get the same thing. Yeah, that's all it was, in general, too. When you write it down more generally, you're gonna. That's all I did in the more general case as well. So like either k or n minus k is smaller, and you'll have a few extra terms, but they're going to cancel on the top. Man, I don't know why this is getting ink all over me as always. This is why I only use a couple particular fountain pens. There it goes. All that ink. Cool. Yeah, that's the way I did it. I guess that's all he meant. I'd always draw a little in my math notes. Usually it was a frowny face with lots of confusion, actually, for most of my life. But sometimes there's a smiley face at the end. Grassmannian, what the hell? Alright, so 6011 we definitely did. Not bad. I don't know if I did a great job explaining it. But if we... Yeah. I'm just trying to see if I have enough to like edit later so it'll be a coherent explanation on 60.11, but I think I do. Could try to move on. Majorant series. Let's at least read it. Suppose you have a sequence of complex numbers. Oh, okay. Of complex numbers and non-negative real numbers. Let A be the series formed. I realize I froze, but I haven't moved, so it's lucky me, I guess. So we've got two polynomials, A and P. P, I guess, is, well, it would have been real, except that you're plugging Z in, so maybe it's complex again. Damn it! Hold on. My connection did not reset. Quit messing with me. There we go. All right. So yeah, we got these polynomials. We have complex A's. The coefficients are complex. Real P's. If the complex numbers are bounded by the reals, we can use this notation. Okay, sure. And we say P is a majorant of A. Okay, sure. Or A is a minorant of P. Fair enough. If A is a minorant of P and its conjugate is as well, then their sum is also majorized, and their product as well. Huh. And then it looks like what a specific case he says for any positive integer, 1 plus z, well, you know, the usual, is majorized by e to the z. Huh. Okay. That's interesting. What can I do with that one? If I have 1 plus z over n to the n, I guess we could look at a series like this, right? Eesh. I mean, we know that in the limit it's bounded by e, but they're saying that these coefficients are bounded by 1 over k factorial. Is that obvious? So this is like a majorant. Is that how you write it? There's the stupid page. There we go. Yeah, not really. Not really. It's more like big and little. Yeah. Anyway, so like that. This series is majorized. Oops, sorry, z is majorized by e to the z. Anyway, I would just need to show that this is true, right? Because these are the coefficients for e, right? I believe this is true. Yeah, sure. Good. So I would just need to show that this happens. I mean, this is just the top terms of... Oh, yeah, of course it does. It's less than 1. Okay. Wow. All right, so that one's not bad. 62. 62 is almost obvious if you know Taylor series for E. I mean, it is pretty obvious, right? So this is less than 1 over k factorial is what we're supposed to be showing. But when you divide this... Oh, I'm sorry, I missed this term. This is there. It's kind of important. So you're just looking at k factors like n minus 1 down to n minus k plus 1. But downstairs you have an n. You have k factors of m. So this is definitely less than or equal to 1. So that proves 62. 61 was the one about conjugates. He was like, well, he gives the whole basic definition, and then he says if, so A was the one with complex coefficients. If A is a minorant of P, so what else did he say? There was another condition besides just these two. Huh, maybe I'm wrong. Maybe that was the only condition. So 61. Oh yeah, that was the only condition. Okay. So if both A and its conjugate are majorized by P and P's conjugate, then you get the sum and you get the product. Has the same property. Well, I mean, isn't that obvious? It seems obvious for the sum. Like, this definition is just like AK plus AK bar times z to the k. It wasn't a finite list necessarily. Anyway, this is this, and obviously this is less than or equal to, I don't know what we're even doing here. So the first part's obvious. As for the product, well, hold on, let me think about it. Yeah, it's gonna kind of intermix, right? It's not just the product of these, but it may as well be. So yeah, when you do that, you get let's change this to a j, change this to a j. You get ak aj bar, z to the k plus j, and then you're gonna have to re-index this. So this is overall kj's, but you're gonna let k plus j be n, and then replace one of them. So this is the same as, it's gonna do kind of an obvious thing. I mean, I guess I can just write n here if you want. But anyway, j is n minus k. So we're going to get ak a n minus k bar. Again, these go from, well, hold on. J was 0. So you could make this a little more clear. This is not bad. This is fine. You can say 0 to infinity, but it's actually not quite right. You get this some sort of diagonalization thing. Anyway, blah times z then. So that's what you get for the product. This is the product. But we also know that this is less than pk, So, again, I wonder what he has to say about 61. There's nothing to show here. 61 is just pushing some symbols around. Follows the definition. For the product, use 34. That's true. So back on 34, that's what I just 34 tells you if you take a product of two series, it has you verify what you would get. So this Cn, you can't read it now. The Cn, that first line, is a formula for the coefficients. That's what I was mumbling about. We could be a little more, rigorous about the statement of what the indices are, but it's kind of obvious. Basically, don't let n be negative, or don't let n minus k be negative, is what I should say. All right, so 61's obvious. 62 is pretty straightforward. Let's see what he has to say. And we have moved a page. I can't believe it. We have successfully completed another page. And some funky thing going on with the binding. I'm gonna get my inky hands all over it. 62 says, what? What? Huh. I wonder if, so I just used the binomial theorem. I don't think that's a problem. He used his high-powered machinery instead, right? It makes me wonder if I'm completely blanking on, I assumed that for example, I assumed that with complex numbers, they're all going to commute as long as you have a real power. This is a real number. It's not a complex number or anything. But am I missing, like, am I missing some crazy basic fact about like, is this not true for complex numbers? That might be why he proved it in a much different way. Let me see something. Yeah, I don't care about. Like, I know you don't have the same power properties, exponent properties for complex numbers as you usually do. You can't just like take them for granted, which I guess is what I did when I tried to use the binomial theorem. But my question is this wrong? I don't really see why it would be. Grr. Well, this is pretty basic stuff. I guess yeah, it should be fine. But like, why wouldn't he just do it this way? Like, part of what I'm curious about is I know there's ways to make mistakes when you're using complex numbers and you're just raising them to powers all willy-nilly and not thinking about it. But I thought that was usually because you've got complex powers, not real powers. And of course, I can't think of any examples right now. But yeah, you should get the usual, as long as these are real numbers for sure, you should get the usual algebra properties, even if this is complex. So like, why wouldn't the binomial theorem work? Seems like this works fine to me. I don't know, I'll have to think about it. I think I'm gonna have to move on for the day, ladies and germs. What's coming up? A little preview of next time. I'll try to address 62 if I have an explanation for it. If, you know. But yeah, maybe we can handle 63, 64 next time. All right, ladies and gents, I will disappear. Have yourself a fantastic day. Thanks for tuning in, everyone.